Today, we're going to tackle a question that sounds simple on the surface, but is actually, well, it's incredibly deep. If you're standing on top of a hill, what's the absolute fastest way to get to the very bottom? We're going to be unpacking a really fascinating PhD thesis that dives headfirst into this exact problem. Now, you might think this quote is from some famous explorer's journal, but it's not. It's actually from the acknowledgments section of the very thesis we're talking about. And honestly, it just perfectly sets the stage for what we're about to get into, not as some dry mathematical puzzle, but as a real human quest to find the limits and discover the very best way forward. Because you know that urge to find the best path, that's not just for hikers. It's the whole idea behind a field called optimization, and it's quietly running our world, from the AI that's probably in your pocket right now to how we develop new medicines. All right, so to find the fastest path, we've got to start by understanding the slowest one. And in the world of optimization, that journey kicks off with a very, very careful walk. So what even is optimization? Just imagine you're standing in this huge, sprawling landscape of hills and valleys, and your only mission is to find the absolute lowest point anywhere. That search, that whole process of finding the bottom, that's optimization. And it's the big challenge this research is trying to solve. So the classic method, the one everyone starts with, is called gradient descent. And the idea is super intuitive. Picture our hiker, but now they're in a super thick fog. They can't see the whole map. All they can do is feel the ground right under their feet. So what do? They feel around, find the direction that goes down the steepest, take one little step, and then they do it again, and again, and again. And look, this method works. You will get to the bottom eventually. But here's the problem the thesis points out. It is slow, painfully slow sometimes. It's safe, sure, but it's not fast. And this leads to the huge question that really drives all the research we're talking about today. Can we do better? Is there a faster way? Yes, we can. And the first big upgrade is to stop walking and start rolling. This was a massive leap because it shifted the thinking from a static, step-by-step process to a dynamic one based on physics by bringing in the idea of momentum or inertia. So instead of that careful hiker, I want you to picture a heavy bowling ball. As it starts rolling downhill, it picks up speed, right? It builds momentum. And that momentum helps it just blast right over little bumps and accelerate like crazy down the steep parts. Way, way faster than our one-step-at-a-time hiker. The thesis calls these things second-order inertial dynamical systems, but really just think heavy rolling ball. But of course, there's a catch. There's always a catch. Speed creates a whole new problem. The thesis points out that these methods can exhibit many small oscillations. The ball is just moving so fast that when it gets to the bottom of the valley, it doesn't just stop. Nope. It shoots right past the lowest point, rolls up the other side, and wastes a ton of time swinging back and forth before it finally settles down. So yeah, we're faster, but we're also kind of reckless. And this is where the real magic happens. This is the core breakthrough of the research. What if we could give our rolling ball a set of smart brakes, a way to keep all that awesome speed, but add the intelligence to know exactly when it needs to slow down? The secret ingredient for these smart brakes is a mathematical tool called the Hessian. Okay, don't let the fancy name scare you. In simple terms, the Hessian is like a super-powered sensor. It doesn't just tell you how steep the ground is, it tells you the shape of the ground. Is it curved like the inside of a bowl, or is it starting to flatten out? And that leads to the big idea, the huge what if. What if we could use that information from the Hessian to control our speed, to create what the thesis calls geometric damping? What if the ball could feel the terrain starting to flatten out and know that the bottom of the valley is coming up? And here's how it works. It's actually a pretty elegant three-step process. First, the algorithm uses the Hessian to sense the curvature of the landscape. As it gets closer to the bottom, the ground naturally gets less curvy, right? It flattens out. Second, using that information, the algorithm applies a super precise braking force, the smart brakes. The flatter the ground gets, the harder it hits the brakes. And third, the result is a perfect smooth landing. You get all the speed with none of the wasted back and forth. So the theory is brilliant, right? A rolling ball with smart, terrain-aware brakes. But does it actually, work? Well, the research puts all of these methods to the test in a head-to-head race to the bottom. And wow, this table tells you everything you need to know. The slow walk, gradient descent, it gets there, but it takes its sweet time. The wild ride, the inertial methods, they're faster, but they're all over the place. But the new method with Hessian damping, it achieves exponential convergence. Let me be clear, that isn't just a little bit faster, it's a completely different class of speed. It's like going from a bicycle to a rocket ship. And if that table didn't make it clear enough, just look at this chart. It's not even a fair fight. If our slow walk is the baseline, yeah, inertia gives you a nice boost. But look at Hessian damping. It is a total game changer. It represents a massive, massive leap forward in how fast we can find that best solution. The thesis actually shows us what these paths look like, and it's pretty much exactly like our analogies. Gradient descent just kind of meanders its way down. The standard inertial method swings back and forth like a pendulum, but the new methods, they trace this beautiful, smooth, direct arc right to the target. It's the difference between taking the winding scenic route and just taking a bullet train straight to your destination. So, a faster way down a mathematical hill? Who cares, right? Why does this actually matter in the real world? Well, it turns out this isn't just some academic exercise. This quest for speed has some seriously profound implications for all of us. Think about it. Every single time you train an AI model, what you're really doing is running an optimization algorithm, searching for the lowest point of error. So, faster optimization means faster, more powerful AI. It means we can simulate how new drugs might work way more quickly. It means designing more stable financial systems. It means we can start to solve these gigantic scientific challenges that up until now were just too slow to even try to solve. So that initial quote about seeing how big the world was, it turns out it was true in more ways than one. This kind of research literally expands the map of what's possible. It gives us a faster vehicle to explore more complex problems, because the faster we can find the best answer, the bigger and bolder the problems we can dare to solve. What's next? Well, that's the exciting part.